Hi everybody, back to Cook You RT again. What I'm going to do today, I'm going to show you how to solve problem RLC circuit, second order or circuit by using Laplace transform. Let's get started with the basic concept of each electronic components. In this case are resistors, capacitors, and inductors. So the concept of a Laplace transform is to make you easier, to be able to analyze the circuits. Or in the term, if you have circuit, you want to find a certain voltage drop at each components, or the current flowing in the circuits. You simply apply Laplace transform. You can write equation for current, or you can write equation for voltage, and then you apply Laplace transform to get in equation in the frequency domain, and then you want to find the current in the time domain or the voltage in the time domain. You simply apply invert this Laplace transform back, and you can get the current or the voltage in the time domain. So let's take a look at the concept of Laplace transform. When you have any function, if that's depend on time, or is the time domain, and then you apply a Laplace transform, you simply get the function in frequency domains, which is represented in the term of as some people used j omega to represent as. And then for the Laplace transform, you simply integrate, take the lower limit from 0 to upper limit or infinity of that function, multiplied by exponential negative st, and then multiplied by dt. And then you end up with something that you have no t term, right? You simply have only your s term. So that's the basic concept of doing Laplace transform. For example, if you have the function in equal to the unit step function, and you know that the unit step function, when the term less than 0 is give you a 0, right? But when the term is greater than 0 or equal to 0, you have ut equal to 1. That's why I have the plot, just like here. Now, if you want to try, by yourself, I just show you a basic example. Later on, you can do the Laplace transform of, more complicated function. For example, sinusoidal function or cosine function. So you just plug in ut as the function of ft multiplied by exponential negative st dt. And since you have a lower limit start from 0, so you can represent ut by 1. And then you do integration. You end up with negative exponential negative st over s. Take lower limit to upper limit to infinity. So that's why you have 1 over s right here. So you take a look at the Laplace transform table. When you do Laplace transform of unit step function over 1, you have 1 over s. Okay, so you can try something just like practice. If you have function equal to psi of at, the Laplace transform of function of psi of at equal to a over s squared plus a squared. Now let's get back to basic circuit components. You start with resistor. You have the current flowing through a resistor. It's IR. The time domain here is represented by IRT. So from Ohm's law, you have a VRT equal to ART multiplied by R. Now for the frequency domain, you know that R doesn't change with the frequency. So when you apply a Laplace transform on the left, you simply change VR, the time domain, to be the frequency domain. In this case, is S. And you use the capital letter, right, V, to represent that this is the Laplace transform. On the right, you do the same thing, so you end up with the I of S multiplied by R. This is in the frequency domain of R, so nothing changed, for you take a look at the circuit here. Now for capacitor, you have one capacitor here. You have the current flowing through the capacitor equal to RCT. You have equation RCT equal to C differentiate of the voltage across the capacitor VC T over by dt. Now for the frequency domain, you are applying the Laplace transform. On the left, you have IC as that's represent the frequency domain. And for the Laplace transform of the differential, the first order differential, you end up with S multiplied by Vc in the frequency domain, and then minus V of C in the time domain, but at t equal to 0. Also, you can say this is the initial condition, right? Now you take a look at the circuit. You have IC here, the current flowing through a capacitor. And then you take a look at the equation here. You have our incoming current equal to IC. And you have two terms on the right. So this is the equation for current. So this term have to be current as well. Vc is the voltage drop across the capacitor. So that's mean from Ohm's law, I equal to V over R, right? Or in this case, you can say V over Z, which is the impedance of capacitor. So you know exactly that the impedance of the capacitor here is become 1 over Cs. And it's agree with the impedance of capacitor equal to 1 over J omega what? C, right? And you represent this one by S. So that's why you have Cs, 1 over Cs here. So you have the current flowing out. You apply K CL at this node, right? Incoming current have to be equal to outgoing current. So basically you have this equation here. This is the current equation. So you have incoming current, right, equal to outgoing current. You take a KVL that's at this node. So you have two current, flowing out. But from this equation here, you have one current right here, and you have one current right here. But this one is become a negative current. So the voltage drop across capacitor is equal to VCS, and this is the divided by impedance of capacitor. This one you have negative sign, so it's act like the current source, which is equal to C multiplied by Vc, or t equal to 0, or the initial condition, or the voltage drop across capacitor at t equal to 0 when you just close the switch. And if you don't have a VC at the initial. This term going to be your 0, right? So you don't have this one. But since this one you have a negative sign here, this means that it's going to act like current source, but moving from the left to the right. Okay, so that's why you have a equivalent circuit for a capacitor in frequency domain look like this. Now let's move to inductor. You apply the same concept, you probably be able to figure out, what is equivalent circuit look like. For inductors, you know that the voltage drop across the inductor VL equal to L multiplied by differentiate the current with respect to T, or dl IL by dt. You do a Laplace transform. You have a VLS equal to L multiplied by the Laplace transform of the first derivative of ILT. You end up with SIL minus IL t equal to 0. This is in the time domain, but this one in the frequency domain. Now you do the same thing. This is, you consider is you apply KCL, right? Incoming current equal to outgoing current. So you need to change the equation in the form of the current equation. So you rearrange your equation. You have ILS equal to VS over SL. You have SL here, and then plus, right, IL at t equal to 0 divided by S, because you have S here in front of our IL. Now you take a look at the equation here. You have the current flowing through our inductor equal to ILS in the frequency domain, and this term had to be current as well. You have voltage drop across the inductor is VL, so you divide by impedance of inductors, which is the J omega L, right? So your J omega is simply S. So that's why I have impedance here, SL for inductor. And this one have to be the current source. And you have positive sign here, so the current source is flowing from the left to the right. So it's become outgoing current. Consider the node here. Finally, you have equivalent circuit for inductor in the frequency domain. You compare to the time domain and the frequency domain. It's going to look like this. Okay, so just mention a little bit about the equivalent circuit of our components in frequency domain. Now let's try some problems. I have circuit look like this. At time equal to 0, I close the switch, and this is going to be your second order circuit because you have two inductors, and no initial energy stored in the circuit, or IL at t equal to 0 equal to 0. So this one, it doesn't do anything in the problem. Phi I1t and I2t for t greater than 0 by using a Laplace transform. Okay, let's move on. Now for inductor, you have VL equal to LdIL by dt. You apply Laplace transform. You have this equation, but at initial condition, you have IL at t equal to 0 equal to 0. So you end up with VLS equal to SL ILS. And also for the voltage source, we want to work in our frequency domain. So you have the DC voltage 336. Sorry, I just look like 336 multiplied by unit step function, right? Because you have no supply voltage at t less than 0, but you close the switch at t equal to 0. That means you connect the supply to the circuit. And you know that you do a Laplace transform of your supply voltage. It's going to be the Laplace transform of unit step function, which is equal to 1 over s. That's why I have 1 over s right here, or 336 volt divided by s. Now redraw the circuit in frequency domain. So the voltage source is turned out to be 336 over s, and the impedance of our inductor has become 8.4 s, and this one become 10 s, but R still be the same, right? It's the frequency dependent. I have I1 right here, and I have I2 right here. Now you apply a KVL, start solving the problem. You apply a KVL at loop 1. I have loop 1 right here. So you have our supply voltage 336 over S, so it's going to be equal to the voltage drop across L, and then drop across the 42 ohms resistor. So that's why I have VL and VR here. You apply Ohm's law, V equal to IR, so I have I1 multiplied by the impedance, which is the 8.4 is I1. And then now you need to find the current flowing through 42 ohms resistor. You have current I1 coming in, you have the current I2 flowing out at node 1. So what you have left over here is equal to I1 minus I2, right? So you count this current, so you multiply by 42, or you rearrange the equation, so you have equation number 1. This is 42. Now for KVL of loop number 2, you do the same thing. You have no supply voltage, so you have 0 here. It's going to be equal to voltage drop across this inductor plus the voltage drop across the 48 ohms resistor plus the voltage drop across the 42 ohms resistor. Now for inductor, you have I2 here. So I have 10s I2. 10s is the impedance of inductor. And you have a 48 multiplied by I2. But when you are for 40 ohms resistor, you have a coming current here flowing through resistor here equal to I1 plus I2. Sorry, I1 minus I2, right? But since you work out this way, clockwise of the current, so that's mean you inverse. Sorry, you need to put negative sign, because it's on the opposite direction. So that's why I have I2, minus I1 here instead of I1 minus I2. Also, you rearrange the equation. You can write I1 in the term of I2. Okay? And you simply substitute I1 into equation 1. Okay, in case I want to find I2 first. Now let's move on. Well, this is just math. So you plug in, or you have 336 over S and then you have 8.4s plus 42, which is I'm missing here, sorry about that. And then you put I1, this term right here, and then you still have a negative 42 I2 right here. Just rearrange the equation to find I2 in the term of S. Finally, I have our I2 or in the term of S equal to 168 over S to the cube plus 14S squared plus 24S. And I work out. I have enough with this term. Now you need to do something like the partial, right? That means you split this one out. Since S have the power, the maximum power is 1, this one is maximum power of S is 1, this is the maximum power of S here is 1, so you can write, this in the term of A over S plus B over S plus 2 plus C over S plus 12, because soon you're going to do inverse Laplace transform, and you know that when you the inverse Laplace transform of 1 over S plus A equal to let's go to the Laplace transform table here. Because you have a inverse of Laplace transform of 1 over S minus A equal to exponential AT, right? This is negative, but you have positive here. The frequency domain turn out to be the time domain if you do the inverse Laplace transform. So that's why I want to write, this term into the partial, like this. Now the problem is to find, I will show you the easy way to find A, B, and C, which is a constant. To find A, B, and C, what you need to consider is you need to find pole, or the denominator, which cause the denominator is that cause the denominator to be 0, because when you have something divided by 0, it's undefined, right? For this term, you have S equal to 0, you have problem. This term, if S equal to negative 2, you have problem, because it gives you 0. And also this one, S equal to negative 12, you have problem. So that's why we have 3 poles: 0, negative 2, and negative 12. And I will show you the way to find the constant A, B, and C. Okay, to find the constant A, you take pole at 0. You multiply by S, because this is pole at 0. So this one cancel out, and you substitute S equal to 0 in these two terms. So you have 0 plus 2, and then 0 plus 12. So you have A equal to 1 over 24. For B, you take pole at negative 2. So you look at this term, so you multiply also by S plus 2. So S plus 2 cancel out, and then you substitute S by negative 2, and then negative 2 plus 12 end up with B equal to negative 1 over 20. And for C, you do the same thing for the pole at negative 12. then have this term, and then do your plug in s equal to negative 12, and this is also negative 12. End up with 1 over 120. So that's why you have I2 as we make agreement. It's become A over S plus B, and then this is your A, this is your B, and this is your C, right? You have C here. 120. 1 over 120, sorry. So you multiply 168 into the bracket. You end up with 7 over S minus 8.4 over S plus 2 plus 1.4 over S plus 12. To find the current of I2 in the time domain, you simply do the inverse Laplace transform of I2 in the frequency domain, or you do inverse, Laplace transform of 3 terms. Same the constant, and then you know that this is the Laplace transform of 1 over S plus A equal to exponential negative AT multiplied by UT. UT is the function. It's change from the frequency domain to the time domain. Right? This is the final solution for you. So you have 7, and then S, you just have only UT is the function. Now you have 8.4 for S plus 2, you have exponential negative 2t UT, and the last term you have 1.4 exponential negative 12t UT. Okay, so this is the final solution for I2. So you can work out for I1. Just repeat the step that we work together, and I give you a solution. It's become 15 UT minus 14 exponential negative 2t UT. I have UT missing here, minus exponential negative 12t UT. So you have I1 and I2. What is where's your I2? This is my I1. This is my I2, right? So you have I1 and I2 in the time domain, look like this. Now let's analyze more. You know that from the circuit, just like straight from the circuit here. For the time into infinity, right? They are in the stable condition, and inductors behave like short circuit because VL equal to L di by dt. IL doesn't change; it stays still, right? So when VL equal to 0, that means the voltage, across, inductors becomes 0, or V2 minus V1 equal to 0. Let's make a V2 equal to V1. So it's just like short circuit, just like a piece of wire. Your circuit turned out to be this circuit. You have nowhere inductor show up. Let's calculate for I1 and I2 for t, go to infinity. Well, you calculate for I1, you find the R total here, which is the 48 ohms resistor in parallel with a 42 ohms resistor, which is equal to 42 multiplied by 48 divided by 42 plus 48. This gives you 90. The current is equal to V over R. So you divide 336 by R total. You get I1 equal to 15 amps. For I2 you use the current divider. You have our I1 is coming in, and it's split. You multiply by 42 if you want to find I2, and you divide by 42 plus 48. You have our I2 equal to 7 amps. Right? This at our t go to infinity. Also at t equal to 0, when you just close the switch, you have no current, I1 and I2, right? Because it's open before. And now you get back to what you have when you solve for I1 and I2 by using a Laplace transform. You'd be surprised. Let's check for t go to infinity. You don't have this term, right? Because this exponential of negative 2t. So this term drop, this term drop. That's why you have 15 amps. Exactly what you have here. For I2, this term drop, this term drop. You have 7, right? And then what about our t equal to 0? When t equal to 0, this term become 1. So you have 15 minus 14 minus 1. This gives you 0. Exactly what you have right here. And when this term t equal to 0, this term become 1. So you also have 0. Okay? So hopefully it's helped you a little bit how to analyze the circuit, RLC circuit, second order system, or you can use this kind of concept for another type of circuits when you have RLC. I'll see you in next YouTube. Thank you.